Boom. All right. So welcome back. So I want to touch base on a couple things from last time. After fielding some questions from several folks, I felt like it probably is pertinent to show you a little more rather than just having the worked out examples for you to look at. So I'll go through this one with it. So as we said, like this is the definition of the derivative. Hey, yay, that's all great. And I had a bunch of examples for you afterwards. And if you read the book, there's a bunch of examples there. But we're going to go through one together just so I can point it out. So we're going to use the definition of the derivative to find f prime of x. F of x is going to be equal to 3x squared minus 5x plus 1. All right. So we're going to start setting it up using the definition of the derivative like that. So now what I'm going to do is I'm going to put f of x in for f of x. And then I'm going to put x plus delta x in for f of x and then put that expression over here. So basically what's going to happen is I'm going to take f of x as you see it, but then everywhere there's an x, replace x with the quantity x plus delta x. Like that. Okay? So f of x plus delta x is this piece right here. And then this is f of x over here. Before I go any further, the goal of this is basically I want to get rid of the delta x in the denominator. By algebraically getting rid of delta x in the denominator, I won't be dividing by 0 anymore, which means this is actually something that's doable and we can work with. So I want to point that out and just so that we're all aware of that. That's our end goal, is to try to get rid of the delta x in the denominator. So at this point, now that I've substituted in the f of x plus delta x, which is the first part of the expression here, and then I have f of x over here, now I'm going to just work on simplifying and see what I can do. Notice that I'm still saying eventually my intention is to let the limit go to 0, the limit of delta x. Eventually I want delta x to be 0. So that's just, yeah, that's what I want eventually. Is it going to happen right away? No, but it will eventually. Because if I let delta x go to 0 right now, I'm going to get indeterminate form. I'm going to get 0 over 0, which is not what we want, like at all. So let's continue from here and see what happens. So I expanded out x plus delta x squared to get this expression. I distributed the -5 to both of those, so I have this. But there's more simplification and expanding I can do before we continue. I could distribute this 3, and I could distribute this -1 over here. So let's do that. Now I'm going to take a sip of water, and I want you to just take a look at that. What do you notice about all of the terms that don't have a delta x variable in them? So take a hot second and look at that. If you notice that all the terms without a delta x have an opposite somewhere in the numerator, you'd be right. Yes, they cancel each other out, Greta. Straight up. You beat me to the punch. Love it. That's the idea. Look at this. 3x squared, -3x squared. -5x, 5x. 1, -1. Every time you're working out the definition of the derivative, everything that doesn't have a delta x should eventually, like, with a polynomial, should eventually go away. If you're dealing with a rational function, they will go away. Most of it will go away eventually, but not immediately. So it's a couple things to be careful of, but generally everything should disappear. Especially, like, you should be able to somehow simplify away a delta x eventually. And this is how it'll work out for every polynomial. So let's see what happens when we can't cancel it all out. Well, looking at that, everything left in the numerator has a delta x. What's nice and efficient about that is we can factor out a delta x. So let's do that. And here's the magic. Because up to this point, If I plugged in 0 for delta x, there ain't nothing you can do. You just get 0 over 0. But now that I've simplified that delta x, if I let delta x be 0, it doesn't blow up anymore. My intention from the beginning was to plug in delta x. And that's why I keep the limit notation with me as I go, is to say, I want delta x to be 0 eventually. I want it to go there. But I want to go to there. But in order for that to happen, I can't do it in the initial setup. The first step, second step, third step, fourth step, fifth step. I can't do it in any of those because I get that indeterminate form. In the sixth step, I lost track of how I was counting. That's a rip. But if you look at this one, I can actually plug in 0 for delta x. And I get 6x minus 5. F prime of x is equal to 6x minus 5. And if you remember the power rule from last year that we started working with, you'll see that makes sense. That it should follow that way. If you don't remember that, that's also okay. We're going to work on that. But that's how that works. I just wanted to point that out because we didn't have that as much time. And from the conversations we had, I had with several folks, this was an important thing that I needed to make sure we spent a little time on. Boom. There it is. There's, again, more examples. There's 2 examples in the post credits of me doing the same sort of thing, working it all the way out. But then I did something else with it at the end. So you should take a look at those. You should also look at the read the examples in the book so you know what's going on there. That said, I want to keep going. Now, 2.1 is the only assignment where you must use the definition of the derivative. You must show all that work every time you find a derivative, unless you've already found the derivative in an earlier problem. I think one of the later problems in 2.1, you need to find a tangent line. Well, the slope of a tangent line can be found with the derivative. And if you already know what the derivative is from a previous problem, you don't have to re-derive it. You're good to go. And it's all good and all to keep doing that. And we can do that wherever a limited or a derivative exists. We could use the definition of the derivative to determine it. But maybe we don't always want to do that. So we're going to look at some basic differentiation rules. Now, this would have a lot more effect if I had been chiding you, making fun of you in class, and you all making me cry and all that fun jazz. So maybe I don't think you're experts on differentiation yet. And that doesn't even make sense because it takes time and effort. And we've had about 10 minutes one day and about 5 minutes today of talking about some other extra differentiation. But we could probably figure this out. There's f of x. I want to know what f prime of x is. It does exist. So in theory, you should be able to use the definition of the derivative to do this. That's all we're going to do today. See? That's it. There's the practice. It says due Wednesday. That's not really true because it's due when you get it done. Again, it's way more effect like in other ways, but let's be reasonable. Let's be efficient and use some rules to do this. Instead of just trying to use the definition derivative on this entire thing and cry and punch holes in concrete, let's not do that. Let's be productive and not just like flood the basement with tears. Let's look for rules and use those rules. And of rules, I mean differentiation rules. This is really a bad joke. I don't know if anyone gets it. It might not make sense. Anyways, I'm going to keep it up there. Yes! Yes! Thank you. I keep putting it up there because I'm like, I wonder how many people remember that. When I was writing differentiation rules, all I could think of was O'Doyle rules. So thank you. Thank you. I've always had faith in y'all, but you just keep reaffirming that. So I appreciate that. Anyways, here are a bunch of differentiation rules we're going to use. These are some basic differentiation rules. In class, I would have you just go look them up online, write them on the table, and then we'll use them. Here's what I'm going to do instead is I'm going to tell you, if you grab your calc book, like this, and if you open up to the front cover, look at that. Basic differentiation rules. There's also basic integration formulas down here, but we won't get to that till much later. A couple of like 2 chapters. Basic differentiation rules. Open up your front cover of your book to this. Now, I would recommend, for just in general about everything I know about learning, that you make this table on your own after class and fill it out. Okay? Maybe include an example for all the for several of them. But you're going to use this table for the next 6 minutes. 6 minutes so I can talk about it. One of these rules is the sum rule. What that means is that when I have, and sum and difference rule, when I have a function that's really made up of a bunch of smaller pieces, I can break up that function, find the derivative of each one separately, and then put it back together. And that's what I want you to do here. I want you to actually find the derivative f prime of x. To do that, find the derivative of each piece, a through f, use the rules in the front of your book, and do the best you can to come up with what you think the derivative of each piece is. I'm going to give you 6 minutes to do that. After the 6 minutes is up, I'm going to show you what I have, and we'll talk through them. All righty? What questions do you have about what I'm asking you to do for the next 6 minutes? Use the rules in the front of the book and try to match up the patterns and do your best to match up the patterns to the pieces I gave you. That's how you're going to do that. All righty? And again, you'll need to try something. Please write stuff down. Do your best. At least if you can identify what rule goes with each part, that will help. And I'll tell you right now, you need to rewrite C and D in order to see them in the table. So think about how you could rewrite those to fit one of the rules. So I'm going to give you 6 minutes. I'm going to let you go. Try stuff. You have to rewrite C and D in order to notice which rule they are. But I want you to try. Go. I also got to check. Oh, that's what I should do. 30 seconds, folks, and I'll be back. Okay. So, let's look. So here's what you should have got as you were working on those. So let me point out each of these. So A, that's your a to the x, or I don't remember what the variable is in the front of the book. But that's the one where it's a coefficient, it's some integer to the power of x, where x is the variable. So there's a rule for that. You just the derivative of this is natural log of whatever the base is times this. So I get natural log of 3 times 3 to the x. The reasoning why that is, we'll look at a future chapter. We're not going to look at it just yet, but it's a rule. I'm telling you it works. I promise it works. And we'll look at why it works later. Oh, shoot. I never said something about that. That's too bad. B, C, D, and E are all what's called the power rule. If you go back to this one, sorry. B, C, and D and E are all either x to the n or a times x to the n. We're using that on all of them, literally that. So the derivative of x to the fourth is 4x to the third. But then there's also negative 16 in front. So negative 16 times 4 gives me negative 64 x to the third. Boom, there it is. This one, in order to do that one, you needed to rewrite it. And now that you see what the answer is, maybe that helps to see. Oh, come on, mouse. Where'd you go? Get. There you are. To get your sweet friggin' time. Is 10x to the negative third. And as soon as you see it that way, it's much easier. I'll look and see. I'll probably have to change my table, Emma, now that I didn't see your question right away, Emma. And I didn't understand what Greta meant, but now I understand both of you. I can figure out how the book has it. This is just how I picked it up online. I forgot to check to see how the book has it different. So we can fix that. Anyways, this is 10x to the negative third. So using the power rule, x to the negative third, the derivative of that is going to be negative 3x to the negative fourth power. And you can see the negative fourth down there. So negative 3 times 10 gives me negative 30 down there. Part D here is done by saying, well, this is really negative x to the 3/2 power. So the derivative of x to the 3/2 is going to be 3/2 x to the 1/2. And since we already had negative out front, we get negative 3/2 x to the 1/2. All right. That's how that bad boy works. E is a more straightforward application. Oh, geez, where'd it go? There it is. A more straightforward application of that rule again. The derivative of x to 1,000, 1,000 x to the 999. But then negative 50 times that gives me negative 50,000 x to the 999 power. And then f is the natural log rule. And the derivative of natural log is 1 over x. So, okay, I can help you with that. We're doing this quicker in a slightly different way than I would have normally. Okay, I appreciate that. Can't stop thinking about the guitar. I was trying to do some different ASMR stuff. Some kids were asking for that in other classes. I'm like, all right, I can try that. And so that's what I was doing there. These, again, we're trying to apply those different things from the book. What was the thing in the front of the book? Pretty sure there was the same setup, wasn't it? Oh, they have the friggin', that's right. That's why I didn't use the front of the book initially. That's why I normally have you look it up online. I just remember the rules were in there. So the things in the front involve the chain rule as well. All right, I can address that. Someone else had already asked for a filled out table. I can include a filled out table for you later of these different rules here. I can fill that out. That's fine. I'm okay with that. I'm more annoyed that I forgot that the front of the book uses the function notation or the chain rule notation that we're not ready for yet. We'll use that later. But the goal, agreed, Tyler. It's much more straightforward than the book. I mean, our book was also, if I haven't mentioned, I'm sure I've mentioned it. The book's older than all y'all. Like, the book is straight up ancient. Like, it's in its senior year of college right now. If it was how long these have been in the district for. Straight up. I don't have a link right now, but if Tyler can pop a link up there, otherwise I can find one later and send it your way. The last thing I need to mention, just real quick, rate is distance over time. A lot of the time that's delta y over delta x. Average velocity is just the change in position over change in time. Instantaneous velocity is the derivative of position. Boom, that should do it. This is just another slide of some connections that eventually you're going to need in the work from today. So it's something, as you get there, you're like, wait, how do I get something from something? Go back and look at this. It's also in the book. You can take a look at that. And here's the practice. It's due soon. It's due later. Let's see how much better those pictures are. Yeah, that's pretty much everything. The only thing it looks like missing, sine and cosine aren't there, and log and exponentials. But those are the basic things. Now, the product rule, quotient rule, and chain rule, we have separate lessons on those, but this is good. This is a good place to start for you. And then it makes a lot more sense than what was in the front of the book. Eventually, the front of the book will make sense. We're, I guess, just not there yet. And that's okay. We'll take our time. Okay. With that said, we've kind of rushed through a bunch of things, and I'll figure that out. So yeah, I want to have more for you, but I think that's pretty much what we have right now. We'll see what next week looks like. I'll let you know once I have a better idea as well. It's online learning. We're going to keep doing the best we can. All right. On that note, send me messages, emails. I'll talk to you later. Got to run to the next class. Sorry, folks.